Hello, everybody. My name is Liz with B.Willow. I am very, very excited for today's presentation. You guys might recall we had our special guest join us last January to do a presentation on Mars. So we are super excited to have Erica back with us today doing a presentation on the asteroid Bennu. So without further ado, take it away.
Thanks, Liz. And thanks everyone who's watching online. My name is Erica Jawin, and I'm going to talk to you today about the asteroid Bennu and the NASA OSIRIS-REx mission that I've been working on for the past few years. So for a little bit about me and my background, I graduated from Mount Holyoke College in 2012. And then I went and worked at the European Space Agency in the Netherlands for a year. And then I got my PhD from Brown University in 2018. And after I graduated, I started what's called a postdoc, it's a short-term research position at the Smithsonian National Museum of Natural History, where I was working on the OSIRIS-REx mission. And then just about 6 months ago, I moved to the National Air and Space Museum, which is still one of the Smithsonian's. And I'm still doing some work on Bennu, and I'm also doing some research on Mars. So all things planetary. And as you may have seen from Liz's note, today, all proceeds are being donated to the Ingenuity Project, which I have worked a bit with. I went to public school. I really believe very strongly in the benefits of a public education. And I'm a huge supporter of the Ingenuity Project, whose mission is to prepare and launch the next diverse generation of nationally competitive STEM leaders from Baltimore City public schools. So that's a little bit about me, a little bit about the Ingenuity Project, but we're here today to talk about asteroids and specifically Bennu. So first off, what are asteroids and why should we care about them? Well, asteroids are remnants of the planet formation process. They're basically building blocks of planets that didn't quite make it into one of the large planets that we're familiar with. These are some of the most primitive bodies in our solar system. And most of the asteroids in our solar system, Liz, can you see my cursor on the screen? Okay, great. So most of the asteroids in our solar system are located in the main asteroid belt between Mars and Jupiter. The asteroids that I study are called near-Earth asteroids because they orbit the sun in a region near to Earth. And so they got to this location because they started in the main belt and got thrown out of the main belt because of gravitational forces of the sun and planets. And now they're orbiting in this region quite close to Earth. And some asteroids, like Bennu in particular, have orbits that cross Earth's orbit, which make them very hazardous because they could actually hit Earth one day. And Bennu specifically is one of the most hazardous asteroids in the solar system that we know about. So it's a little bit of incentive for why we want to know more about this asteroid. So asteroids are very small, but how small are they? So for a little bit of a sense of scale, this little gray blob right here is our moon to scale with Earth. And then if we zoom into the moon, the largest asteroid or the largest body in the asteroid belt is Ceres. But Ceres is actually huge for asteroids. It's actually classified as a dwarf planet, not even an asteroid because it's so large. And so then if we go even smaller, the largest proper asteroid is named Vesta, which is much smaller than Ceres. And then the near Earth asteroids, like the ones that I study, are so much smaller than this. These are some of the asteroids that have been visited with spacecraft in our solar system. So these tiny little boxes here are the size of these near Earth asteroids. There's one pixel in this little box down here called Itokawa. And if we zoom in, this is Itokawa, this sort of otter-shaped asteroid. And this is one of the near-Earth asteroids we've visited in the past few years that's very similar to Bennu, my personal favorite. So these near-Earth asteroids are tiny, but they're weird shapes. They're potentially really dangerous to Earth. And so even though they're so small, Bennu is a little bit larger than the Empire State Building. So if Bennu were to crash into Earth, even though it's tiny, it would still do catastrophic damage to Earth. And so that's one of the many reasons that we sent the OSIRIS-REx spacecraft to go and investigate this little asteroid. But it wasn't just out of fear of being destroyed by this asteroid. Bennu is actually really, really scientifically interesting. So I mentioned that asteroids are these building blocks of planets. Bennu in particular is very rich in organic compounds and water-bearing minerals. And this is really interesting because we don't know where the water on Earth came from, the water in our oceans. And likewise, we're not really sure where life came from, how life developed on Earth. But trying to answer these questions by studying materials on Earth are really difficult because the rocks on Earth have been rained on, there's plants growing all over them. We have plate tectonics that deform them and squish them and shove them back into the interior of the Earth. So the geologic record on Earth has been largely destroyed for rocks over 1 billion or so years old, which seems like it's really old, but actually for geologists, 1 billion years is kind of a young rock, for planetary scientists at least. So if we want to answer questions like, where did our oceans come from? Where did life come from? We really want to go a step further and find out where that material came from before it was delivered to Earth. And so studying asteroids like Bennu give us the building blocks of where that material came from. So if we want to understand how life started on Earth, we have to go somewhere else, like to Bennu, pick up a sample of the materials from this very pristine, very ancient asteroid and bring it back to Earth so that we can study it in our labs on Earth. And so that's why the OSIRIS-REx mission was developed and why it went to the asteroid Bennu. And I keep saying OSIRIS-REx mission. It's this very long acronym that stands for Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer. It's what we call a backronym. You kind of choose the word and then make the make the individual words fit the acronym. But it's a great mission. It was proposed over 15 years ago and eventually launched in 2016. And then we arrived at the asteroid in 2018, which is around when I joined the mission. And then for 2 years, we orbited the asteroid, and this suite of instruments on board the spacecraft took pictures, spectra, looked how light and energy was reflected off the surface, interacted with different minerals. We had a laser altimeter on board that measured the height and the shape and the roughness of the surface, a whole great suite of instruments. And then in mid to late 2020, we collected a sample of the surface. And this actually was delayed a bit because of COVID and other issues with the asteroid. It was, well, we'll talk about it. But it happened in 2020. It was very successful. Well, I'll show you some great images from sample collection. And then in early 2021, the spacecraft left Bennu and started its long journey back to Earth. And in September of 2023, so next year, those samples will be delivered back to Earth, and then we'll be able to start analyzing these samples to answer these types of fundamental questions about life and about the origins of our oceans. And so this image on the left is the official patch of the mission. It shows the spacecraft with its solar panels sticking up and the TAG SAM arm, our sample collection instrument, reaching down towards the surface of the asteroid. This one's good. It's not my favorite patch. I much prefer the original mission patch that's shown here, that I think it gets a little bit more of like the revenge aspect, that we're finally getting one back to the asteroids for what they did to the dinosaurs here on Earth. But alas, this is no longer the current mission patch. It's been so much fun to work on the mission. We've set tons of records. We've actually set 2 Guinness World Records. One is for the closest orbit of a planetary body by a spacecraft. And then the second award was actually given to Bennu for being the smallest object ever orbited. So go Bennu. And so I mentioned that the major overarching objective for this mission was to collect a sample of the asteroid. So how did we do that? Well, I mentioned this instrument called TAG SAM. That's another acronym called the Touch and Go Sample Acquisition Mechanism. And the way that this works, it's sort of like a reverse vacuum cleaner, where it's this cylindrical, like hubcap sized device on the end of a 3-meter long boom, like a 10-foot long arm that reaches out from the bottom of the spacecraft towards the surface of the asteroid. And once the device touches the surface of the asteroid, instead of having a vacuum that sucks air through the device, the TAGSAM head blows nitrogen gas through the head into the subsurface, which mobilizes dirt and dust and rock fragments up into the head of the TAGSAM device. And then you can see in this video here, the gas will exit through a mesh screen, or it did exit through a mesh screen on the device, but all of the dust and the rock particles, all the interesting bits for us geologists, will be trapped in the head. And then after that process is completed, the arm retracts the TAGSAM device, and it reaches back towards the spacecraft and deposits it in the sample return capsule. That's this white little disc-shaped device here. And then the whole spacecraft comes back to Earth. And once it reaches Earth, the SRC, the sample return capsule, will detach from the spacecraft and come through the atmosphere and land, hopefully, fingers crossed, in Utah, where it will go and be picked up by the science team. And then the rest of the spacecraft will stay in space. And fingers crossed, we're convincing NASA headquarters right now to let us send the spacecraft to a different asteroid, which is, I'm happy to talk about at the end, not Bennu, but also should be really interesting. And so this whole process was developed many years, like decades before, not decades, but like 15 years before we arrived at Bennu. And before we arrived at Bennu, we didn't have any resolved images of the surface of Bennu. So we didn't know what it would look like. We had some Earth-based data that told us about probably the composition of the asteroid, a little bit about how rough we expected the surface to be, like the particle size. But it was really interesting for me to learn how you develop an instrument and a whole spacecraft to go and sample material from a body you've never been to. And so the way that this was done was, there was a very similar asteroid that was orbited by a spacecraft about 10 years earlier. And this asteroid is Itokawa that we looked at before. This is, again, a near-Earth asteroid. The Earth-based data suggested Itokawa and Bennu were very similar in a lot of physical properties. And as you can see from this image here, Itokawa is very rugged, these huge boulders, but it does have these nice smooth patches. And so the TAGSAM device can only ingest particles up to a few centimeters in diameter. And so the instrument team said, oh, well, that's fine. We'll get to the asteroid. If it looks like Itokawa, we'll find the smoothest spot on the asteroid. We'll find one of these nice sandy beaches that Itokawa has and find the best of all the good places on the asteroid, and we'll go and sample there. And so that was the plan. But because Bennu threw so very many twists and turns at us, we got to Bennu. And from the very first image that we got, we saw that Bennu is covered in boulders, huge boulders of all sizes. This little boulder down here is about the size of a horse, for context, which I just think that it's kind of mind-blowing. There's boulders of all shapes, all sizes. There's boulders on top of boulders. There's boulders sticking out of the ground. It is insanely rugged. And it was immediately clear to us on the team that there are no sandy beaches on the surface of the asteroid anywhere. And so this is like kind of a really big problem, because the TAGSAM device was designed to collect a sample of material, assuming there was a certain size distribution of particles on the surface, assuming we were going to a sandy beach. If you go and sample some of this material, what can happen is you can wedge a large rock inside that hubcap shaped device and clog it and break the device. And so you risk bringing no samples home, or you risk breaking the billion-dollar spacecraft that we spent 15 years designing and flying, getting all the way to this asteroid. So what do? Do you not collect a sample, or do you try and collect a sample and potentially risk the entire mission? And so this was one of the most interesting professional experiences I've had. The entire science team got together, literally hundreds of scientists and engineers, all working together. And we said, okay, everyone look at every spot on the surface of this asteroid and find anything smooth. It doesn't have to be huge. It could be a tiny spot. It could be a large flat boulder. We just want anywhere that's flat and smooth, and we'll see if we can make it work. And so what we did, we all got together and we actually found over 100 potential sample sites. Some of them were tiny. One of them was literally on top of a flat boulder. And we used machine learning. We had some crowdsourcing. It was this crazy process that took a very long time. And we ended up doing like a March Madness style bracket to see which sites were better than others. And we weighted things like how interesting was the science? How sampleable is the material at this site? Like which site has the smallest particles? Which sites can you get the spacecraft into and out of the most safely with the smallest amount of risk? And we were finally able to whittle this down to a final 4, and eventually our primary and our backup sample sites, which are shown here. The primary sample site we named Nightingale, which is shown in the upper right-hand image, and our backup site was Osprey. And so we had these 2 sites, and so that took a huge amount of work. But also the navigation team developed these 2 really revolutionary, kind of amazing systems that would autonomously navigate down to the sample site and fly itself between rocks on the surface of the asteroid to safely collect a sample. And there was this one program is called Natural Feature Tracking, NFT. And this system was included sort of as just like a backup for our laser altimeter in case some things didn't work. It hadn't really been vetted before. It was just sort of like, we'll just bring it. We'll see how it works. And if it works great, we could use it on another mission in the future. If it doesn't work, it's not a big deal. And it turned out that this was the major thing that we relied on to collect a sample. And the way that it works is you would have people, me and some other colleagues, carefully map every single particle within the sample site. So within both of these sample sites, every tiny little speck you see in these sites is a rock particle. So we would trace the outlines of all of them. And we would feed that into the onboard computer on the spacecraft. And the spacecraft then would start to execute its sample collection maneuver. It would go towards the surface, reach the arm out, and then it would look for individual rocks on the surface, and it would correlate what it was seeing with what we had already mapped. And it would line those up to basically steer itself on the ground and steer between the biggest and most dangerous particles. And so that was the first half. The second half of the navigation was called Bullseye Tag, where we would start going towards the sample site. The spacecraft would start steering itself. If the spacecraft decided it was not on a safe enough trajectory and it was going to crash into the surface, if it didn't do anything else, it would just say, oh, nope, this is too dangerous. I'm not going to do it. And it would, instead of going all the way down to the surface, it would fly in and then whoop, it would leave and would circle around Bennu, and we'd try it again. And that didn't exist before the spacecraft got to Bennu. That was a totally new thing that the navigation team just developed and built into the whole spacecraft. So I'm like harping on this a lot because this is not something anyone expected to have to deal with either of these things. And if we hadn't done this, we wouldn't have collected a sample. We wouldn't have been able to go to any of these sample sites. It's just very cool. So we have our primary and our backup sample sites. The primary sample site is called Nightingale, which you can see here. This is our highest resolution mosaic of the sample site. And the first thing you might notice is that, hey, there's a nice smooth patch right in the middle of this image. The second thing you might notice is, wow, there's still a lot of boulders in this area. It still looks really rough. And yes, you're totally correct. In particular, this one very large, very rough boulder that we nicknamed Mount Doom is 10 meters in diameter, like 30 feet across. It's the height of a 3-story building. And the spacecraft had to fly in directly over this boulder, dive down right in front of it, and gently touch the surface inside this crater and then make its way out without crashing into the building size boulder or any of the other very large boulders in the surrounding area. So without dragging it out anymore, we did do the sample collection. It worked spectacularly well. And this is a video. I'll just let it run. I'll let it go one more time because I think it's really cool. Oh, okay, so this is the last couple of seconds leading up to contact with Bennu. So this is looking down that boom arm onto the tag head. Again, it's that hubcap shaped device that you can see move at the last second right there to orient itself to the surface of the asteroid. And then once it touches the surface of the asteroid, that triggers the nitrogen gas jets to blast into the surface to mobilize material into the tag head. It turns out the surface of Bennu is very unconsolidated. It's very weak. It's just like a pile of gravel with some dust and some smaller rocks. And you can see that because there's this huge cloud of debris that gets kicked up right as soon as we contact the surface. And so that cloud that's kicked up is a little bit because of the gas jets that are blasting through the surface, but more it's because of the thrusters on the spacecraft that blasted all this gas onto the surface to back the spacecraft away from the surface of the asteroid. So you have all of this gas blasting onto the surface, pushing the spacecraft away, but also blowing all of this material up into space around the spacecraft. And it doesn't look like the spacecraft was damaged at all, which is great. It looks like we got a really good amount of material in the tag head. Everything was executed seemingly perfectly. It was great. So the spacecraft did this, brought the arm away from the asteroid. It was in sort of a safe holding pattern orbiting around the asteroid as we analyzed how much material was in the tag head. And because it's Bennu and because there had to be one last surprise, we took some images of the underside of the tag head to see if we could see into it and see how much material was trapped in the tag SAM head. And we saw particles streaming out of the sample collection mechanism. And if you consider that this mission cost $1 billion to bring back a few tens of grams of material, you can just sort of count your money flying back into space with each particle coming out of the tag head here. And so we're like, oh, this is terrible. What are we gonna do? And so quickly, we had to cancel one maneuver we were planning on doing that was to spin the spacecraft around with the arm extended to calculate what's called a moment of inertia. It's basically a way to figure out how much mass was trapped in the tag head. That movement would have thrown even more material out of the tag SAM head. So we canceled that, quickly retracted the head and put it in the sample return capsule and quickly stowed it and made sure that it was safe. But the upside of this is that we think that this leaking tag was because there is a very large fragment of rock that got wedged in the tag head here. And there's this mylar flap that was supposed to close and keep all the material inside, but this rock was so big that it got wedged inside and held it open. So that's why this material is coming out. So it's bad that we lost a lot of this fine grained material, but we lost it because there's this big rock that got wedged in there. So we should hopefully be getting this nice big chunk of sample that's brought home within the tag head and whatever else is left in there. So, pros and cons. So the tag head was stowed in the sample return capsule, which you can see here. Wait for it to click in. Oh, it's so satisfying when it clicks in. And then you can see it's like classic. When it clicks into the SRC, let's see if it'll run again. Okay, here we go. When it clicks in to the SRC, you can see another couple of little pebbles stream off. Like we lost just a couple more little particulates after it snuck in. So it's all secured in the SRC here. We disconnected the tag head from that boom arm, and then the lid of the SRC was closed and sealed. and it is now safe. The samples are not going anywhere. Well, they're certainly going places, but they're not going to leave the SRC. And the next time this will be opened is in September 23rd, 2023, when it lands in the deserts of Utah. It's very exciting. And so this was the end of the orbital phase of the mission. The spacecraft collected the sample. We were ready to head home, but we were able to get one last look at the surface of Bennu after we collected the sample to see how much of a mess we made in the sample collection region. And so this is the site here. It's a before and after image. The X is the spot where we actually touched the surface of the asteroid. And you can see this one rock here got blown tens of meters outside of where it was initially inside the crater. And that was purely from the thrusters from the spacecraft blowing gas onto the surface and making that big cloud of debris that you saw from the video. You can also see that the crater was relatively smooth to begin with in the before image. The after image, there's a lot more exposed boulders on the surface. So the geologists like me are doing tons of science figuring out, are there more large boulders in the subsurface? Is there some sort of process that concentrates fine material at the surface and larger material in the subsurface, or vice versa? Because there's big boulders everywhere else. Why are there fine-grained materials? How did this crater form in the first place? There's all kinds of great science questions that you can ask. So that's a very brief overview of the OSIRIS-REx mission, our sample collection process, and there's so many great things that we're expecting to see when we open up the sample return capsule and get our samples into the labs on Earth. So for some closing thoughts here, exploring Bennu has been really surprising. I mean, I'm an early career scientist, so this was the first active mission that I worked on, but even for the grizzled old scientists who've done missions before, this whole experience threw us a lot of curveballs. I hope that I conveyed that asteroids are scientifically valuable and are targets for future missions. There's 5 or so upcoming missions that are going to asteroids, some that are like Bennu, some that are completely different from Bennu. We're crashing a spacecraft into an asteroid to test deflection technologies for planetary defense. There's another spacecraft going to Psyche, a metal asteroid that could be the core of an ancient planet. There's so much cool science you can do with asteroids, and it's a really exciting time to be in the whole field of small bodies. And from the Bennu perspective, there is so much exciting science to come in 2023 and beyond. And because I get this question a lot, we've been through a couple of hard years. I did mention that Bennu is a very hazardous asteroid, that it could crash into Earth, but we've all had it hard enough. We don't need one more thing to worry about. We don't need to worry about Bennu. Yes, near-Earth asteroids are on unstable orbits. And if Bennu were to hit Earth, the energy released would be absolutely massive and catastrophic. But the actual quantified probability of Bennu hitting Earth is 0.037% probability that it would hit Earth only during the years 2175 to 2196. That's a 1 in 2,700 chance that Bennu is going to hit Earth. And Bennu is the number 2, like the second most dangerous asteroid that we know about in the solar system. So that means that there's only one other asteroid that is more dangerous than Bennu. And Bennu is, like, in all reality, not that much of a hazard to us. So don't worry, we're fine. Everything will be fine. Bennu is not going to crash into us. Although I will note that the number 1 most dangerous asteroid is called Apophis, which is where the OSIRIS-REx spacecraft might be going to after it delivers the sample to Earth in 2023. And Apophis is also not going to crash into us, but it is going to pass between the Earth and the Moon in 2027. And it was the closest that any large asteroid will ever have come to Earth in recorded human history. And you'll be able to see it with the naked eye at night on about half of the Earth. So that one's going to be really exciting. So stay tuned. Again, not a danger, we're all fine, but it will be very exciting when that actually happens. So thank you so much. I'd love to take any questions. And if you do ever have any questions later on, feel free to email me. I always love talking about science. Thanks so much.
Thank you. That was awesome. I feel like I learned so much about all of that. So that was incredible. Thank you. Yeah, I mean, I would just love any more, I guess, information or thoughts you have about kind of what sort of studies will be happening once we do have the samples back on Earth. Yeah.
Yeah, there is a whole plan of hundreds of scientists in all different countries across the globe for these analyses. And there's a lot of very nitty gritty ones that, to be honest, I am not a sample analysis person. So some of those are beyond me. But from the most basic high level perspective, we want to figure out what these samples are. We have all of these images and all these data about the rocks and the material on Bennu, but it's all done remotely. And there's a huge gap actually in our understanding of remote analyses, which is what I do, and sample analysis when you have something in your hand. And actually, this is a huge issue in asteroid and meteoritics, like asteroid science and meteorite science, because we have literally thousands of meteorites in our collection, and the Natural History Museum is home to the National Meteorite Collection. But only a small, like a tiny fraction of those meteorites have been able to be linked to their parent bodies, the asteroid that they came from in the asteroid belt before they hit the Earth. And this is really an open question in the field. We don't really understand why it's so hard to connect this thing that we know came from an asteroid somewhere and actually finding the asteroid. And so one of the biggest debates within the field of Bennu science is, what is the closest meteorite analog that we have to Bennu? And a second question is, do we have anything that looks like Bennu? So we know that Bennu is rich in organic materials and has been very heavily aqueously altered. So it has a lot of water in it. And so there's a very broad class of meteorites that we call carbonaceous meteorites that have a lot of organics and have been heavily aqueously altered. So we think that there is this huge group of meteorites that are similar to Bennu, but there's all kinds of debates. Is this more of a CI chondrite or a CM chondrite, or could it be one of the CM2s that you get branching more and more and more until you are debating, is it this tiny fraction of this sample or this fraction of this sample that's more similar to Bennu? But there's still this option that we don't have anything that looks like the material from Bennu. So that, to me, is the most exciting one that we can look at. And then you start getting into more questions of how old are these rocks? How did they form? When did they form? Can we tease out the interactions between water and rock and heating? And how, like, did the rocks on Bennu interact with other materials in the solar system before it formed Bennu? There's just a huge suite of questions you can get to before we can even get to the questions about where did the life on Earth come from, or where did the water in our oceans come from? So there's literally years of work that we have to do before we can start answering those overarching questions that I posed teasingly at the beginning of the talk.
And something I've been reading in a book about lichens is all the experiments that have been taking lichens, out into outer space, bringing them back and seeing their survival. So I was just curious, do you know offhand of any research specific to lichens with?
No, to be perfectly honest. There's the field of astrobiology is exploding these days. There's so much research about how life formed, could have formed and evolved or not on other planetary bodies. And it's been so interesting over the last 5 or 10 years with all these experiments going to the space station and bringing lichens, but also tardigrades, water bears, these extremophiles up into space environments and radiating them and basically putting them outside of the space station and putting them in the harsh radiation environment of space, and then seeing if they could survive, right? And so some of these are for theories of what's called panspermia, that life could have started somewhere else and then been delivered to Earth. But also there's also a part of it, not to get too deep down a rabbit hole, there's a whole branch of NASA called planetary protection that deals with issues of contamination, forward contamination and backward contamination.
Yeah.
And so this is an issue that we have to deal with when we go to planets like Mars or Europa, places that currently or in the recent past hosted liquid water where life could have developed or could be developed. We need to be very conservative about the contamination on any kind of spacecraft or instrumentation that we bring there, because if there are terrestrial microbes that we accidentally introduce into a habitable environment, we could be introducing life to other environments that could then colonize and naturalize on those planets without meaning to. And so all of this research in astrobiology about lichens and tardigrades and extremophiles are interesting from both perspectives. So like, where did life come from, but also where could life go, either intentionally or completely by accident?
Right. Yeah. Wow. Truly fascinating. Well, we'll have to have you back. So 2020.
Happy to do it.
I guess how soon after its return do you think there will be some sort of information ready to be shared? Or yeah.
Pretty quickly, because there was another mission that flew sort of contemporaneously with OSIRIS-REx from the Japanese space agency, JAXA. And so they sent this mission called Hayabusa 2 to an asteroid called Ryugu, and Ryugu and Bennu are believed to be very similar. And so the missions flew at the same time, and they had not the same instrumentation, but complementary instrumentation. And both missions collected samples to bring back to Earth. And the Hayabusa 2 samples actually were recently just delivered to Earth, I think in October of last year. And we are already getting our first results from the Hayabusa 2 team. So I was at a conference this past week, and there's two whole sessions on initial observations of samples from the Hayabusa 2 team. And so it's really exciting. They're starting to do the type of research that the OSIRIS-REx sample scientists will be doing on the Bennu samples. So within a couple of months of getting the samples back, I would say, expect to see your first science headlines.
Very exciting times with this and James Webb, and yeah, it's very exciting.
Yes.
Well, thank you so much. Just making sure we didn't get any questions on Facebook. I don't think we did, unfortunately. But thank you, Erica. And
no problem.
If anyone has further questions for you, we've got your email up there, but we would also be happy to put people in touch. And yeah, excited to follow up with you.
Thanks so much, Liz.
Yeah, thank you. Enjoy your day.
You too.
Bye.
Bye.